Um, so last time we talked about moments and couples and the rotational version of Newton's second law. Today, I'm going to do a couple of examples to motivate our discussion of joints. So I'm going to talk about what kind of loads are applied by different kinds of joints. Um, so first I'm going to do an example. Oh, anyone have any questions from last time before I start? Okay. So let's say that we have a cantilever beam that's it's straight though. Ooh, that's even worse. Um, so it's glued or fixed to the wall. It can't rotate or translate. And there is a force acting like this of 500 newtons and a force acting like this of 1,000 newtons. Whoops. Like this. And each of those is at 30 degrees. And the lengths that we need, there's 1 meter from the wall to this first force and 1 meter from the wall to, or from the first force to the second force. And this joint is called a fixed joint. A fixed joint, it doesn't allow any translations, right? I mean, you try to move this thing to the left or the right or up or down, and it won't do it. And it doesn't allow any rotations. So it makes sense that in order to prevent translations, you're going to need to apply forces, right? Force components. And in order to prevent rotations, you're going to need to apply rotation components, moment components, okay? And it's actually couples. So a fixed joint applies a full force vector. What a full force vector is depends on whether you're in 2D or 3D. In 2D, that's just two components. And a full couple vector. And because of that little example I did last time, when I talk about a couple, I'm just going to represent that as a pure moment that doesn't have an about point associated with it, okay? So that's just a moment that we're just going to add to all the rest of our moments in the rotational version of Newton's law, no matter what we choose as our about point. So that's a couple. And we want to calculate the reaction loads at the wall. What are the wall reactions? So we want to find that force vector, and we want to find that couple vector. In 2D, that couple vector just has one non-zero component, the z component. Okay, so it's 3 non-zero values that we want to find in a 2D problem. Okay, so before we can use Newton's laws, we have to start with a free body diagram. And this is not a free body diagram, right? I said before that a free body diagram in this class has to be nothing but an outline of your isolated object with loads acting on it. So here's the isolated body, and the loads are 500, 1,000, And then I'll put a coordinate system here. And there's also a load, a force that I'll say is acting right there. And that's the force applied to the body by the wall. And since that's a vector, I'm going to use that. Since it's an unknown force vector, I'm going to use that subscript notation. So on the body by the wall. And then there's also a couple applied by the wall to the body. I'll represent it like that in 2D. In 3D, by the way, I'll represent couples like this with little doubled arrows to so that's if it's 3D. Okay, that's a full free body diagram. So now I'm going to go on to, we're going to go from here to Newton's second law and the rotational version of Newton's second law. In order to do that, I'm going to fill out that table that I talked about with moments, and we're going to see how that just makes it really, really easy to, maybe I already did an example like that, but filling out that table just makes it really easy to fill out the left side of both of those Newton's second laws. Okay, so for each load on this body, we're going to enter where it's applied, the about point for calculating our moments, because we need to be consistent with our about points for all the moments. And then the row vector, which is p minus a. Then the force vector, and then finally the moment about a. So I'll just start over here and work my way to the right. I guess I'll start with that couple. I haven't named it yet. Let's call that M, the moment on the body by the wall. Okay. And in fact, so when I use couples, if my couple is represented as a vector variable like this one is, well, I'm being a little, in 2D, the equivalent of a full vector unknown couple is just a single value. So I'm writing this as just a scalar, but anyways, couples also obey Newton's third law. So if you have a couple applied to B by W, that's equal to negative couple applied to W by B. And that's why I'm going to use that subscript notation on the couple. And it makes sense that that would hold, right? Because these couples, even though we're treating them as just pure moments, they really are just combinations of forces. And you know that equal and opposite applies to every force, so it has to apply to the couples as well, right? All right, so let's start with the couple. That's applied at the origin, so I'll go 0, 0. We have to choose an about point. It makes sense to choose an about point that's at some unknown load, because what is that? What's the benefit of that? Like,
that falls away.
Yeah, that's right. So if you have like an unknown force, if I put my about point where this FBW acts, then the moment produced by FBW is 0, right? Because there's row vector is 0. And therefore, that unknown force vector doesn't show up in your moment equations, and it just simplifies things. So put your about point where you have an unknown force. So 0, 0. Then rho is this minus this, so 0, 0. Force vector, we're not talking about force vectors here. And so the moment is m BW. And that's the moment about anything because it's a couple, so it's the moment about A produced by that couple. Okay. Now we'll go to FBW. That also is applied at the origin. The about point. Now notice on any one of these tables associated with a free body diagram, your about points for every load are going to be the same thing, right? So rho has to be zeros. The force vector here is FBWX, FBWY. And then the moment applied by that force about, yep. Now this force, that acts at 1, 0, right? 1 meter over. The about point still has to be 0, 0. And of course, you don't have to, there's nothing that says your about point has to be the origin, okay? We could have made the about point 50, 50 or something. The one thing you just do have to do is whatever your about point is for this, it has to be the same for this and this and this. So 1, 0 minus 0, 0 is 1, 0. That force is, since that's 30 degrees, we have negative 866, negative 500. And now this is going to be our first non-zero moment about A. 1 times negative 500 minus 0, so negative 500. And then the last one is this 500 Newton force. That's acting at 2, 0. The about point is still 0, 0. Rho then is 2, 0. If you do that trigonometry for that 30-degree angle, you get negative 433 and negative 250. So 2 times negative 250 minus 0, so another negative 500. Any questions so far filling out that table? Any statements of fact or frustration? Humiliation? Mike? No? Not yet. Okay. All right, so now we're going to go from the table to the two versions of Newton's second law. First, the translational Newton's second law, the real Newton's second law. And in order to put these force vectors on the left side, you're just going to go straight down the force column of this table. So we have FBWX, FBWY plus negative 866, negative 500 plus negative 433, negative 250. That's all the forces. So since it's in static equilibrium, that's all equal to 0. Otherwise, it would be equal to ma. And then the rotational version of Newton's second law about A. Now we're just going to go down this side. And if it's a 3D problem, these will have to be represented as vectors. In a 2D problem, you know, in my other examples, I put everything as 3D vectors with just zeros in the z component. And then we had 3D vectors here, where the only non-zero component was in what? Z, right? So it's fine with me either way you represent it. So for the left side of this, we have MBW minus 500 is equal to 0. So that's 3 equations, 3 unknowns. And this one you don't have to really solve as a system. Every equation just has its own variable. So we get the force vector FBW is equal to positive 1300, positive 750, and that value, the value of that couple, the moment produced by that couple, MBW, is equal to 1,000 Newton meters. Okay, so let's interpret this. This force on the body by the wall is mostly to the right. I'm still working on right and left. And also somewhat up, right? So let's look at the picture and make sure that makes sense. These forces are pushing down and to the left. So in order to counteract that, there have to be forces to the right and up. So that makes sense, right? And then look at the couple that's applied. Well, both of these, you can imagine, would tend to rotate this body this way, right? Which would be a negative moment component. So to counteract that, we need to apply a positive moment, a counterclockwise moment. And that's what we have. Positive couple applied by the wall. And then if you wanted to know what's the force applied to the wall by the body, it's just negative of this. So negative 1,300 newtons, negative 750 newtons. And how about what's the moment applied to the wall by the body? That's just the opposite of this, negative 1,000 Newton meters. All right, let's do another example. So this time, we have a beam that's attached to the ground by a hinge joint on the left, and it's attached to the ground by rollers in the middle. Between the end point and the roller, we'll say is 1 meter. Between the rollers and the other end point is another meter. And let's say that there is a force applied at the end at an angle of 45 degrees of 1,000 newtons. Over here, this is a pin joint. And and this one is a roller. So in order to figure out what kind of loads those two joints, the pin joint and the roller, apply to that body, we need to think about how motion is restricted by that joint. The pin joint, it lets any rotation happen, right? So it's not going to apply a couple, but it doesn't let this beam translate this way or translate this way. So this pin joint is going to apply a full force vector to the body. And this roller, if this joint wasn't here, it would allow rotation. I guess you sort of have to think of this as maybe a single, even though they'll often be drawn with multiple wheels or something. You can just think of it as like a single point that it's making contact, okay? And at that single contact, this body would be allowed to rotate, right? So it's not going to apply a couple. This body would also be allowed to translate side to side, left to right, but it wouldn't be allowed to translate up and down. So this roller just applies a single force component it's a force along a line, and this might take a little thinking to make sense of this, but it applies a force along a line that's normal to what it's rolling over, okay? I'll say normal to the ground. So now that we know what types of loads are going to be represented by these joints, we can draw the free body diagram. So there's the beam. We have a full force vector here, and that's the force on the body by the wall. Sorry. Yeah, maybe wall. Since there's no wall, let's call it something else. On the body by the pin. And here, there is a single force applied upward on the body by the roller. And the only other load is this. So now we can go to the table. So first is the point where the forces are applied, the about point, row vector, force vector, moment about A. We have to choose an about point. So by what I said last time, it would make sense to choose an about point here or an about point here. I'm going to choose this one. Can anyone think of a reason why?
2 variables?
Yeah, 2 variables. So there's 2 variables we're getting rid of if we put it here in the moment equation, as opposed to 1 variable here. Yeah, exactly. So our about point is going to be, I'll put the coordinate system here again. So our about point is going to be 0, 0, 0. I'm going to write it all in vector form this time. It all means the same thing as the form of the previous one. So this force, FBP, is applied at the origin. That means that the row vector is zeros. The force is FBPX, FBPY, 0. And the moment is 0, 0, 0. Now the force from the roller, that's applied at 1, 0, 0. The about point is zeros still. So the row vector is 1, 0, 0. That force vector is 0, F, B, R, 0. And so the moment about A is 0, 0, FBR. And then last, this force on the end, that's applied at 2, 0, 0. About point stays the same. The row vector is 2, 0, 0. The force is negative 707.1, negative 707.1, 0. And so that moment is 0, 0, negative 14, 14.2. All right, so now Newton's laws. First, we're just going to go straight down and add up the forces. So we have F, B, P, X, F, B, P, Y, 0, plus 0, F, B, R, 0, plus negative 707.1, negative 707.1, 0, equals all zeros. And then rotational Newton's second law about A. We have 0, 0, FBR plus 0, 0, negative 14, 14.2 is equal to 0, 0, 0. And I did it in vector form that time. You can see it comes out giving you the exact same information, even though we did it as a 3D problem. So we have 6 equations. 3 of those 6 equations are useless because there's nothing but zeros in them, and we just end up with exactly the same thing we ended up with doing it as a 2-dimensional force vector and a 1-dimensional moment vector. So solve this system. This time you don't, it's a system, but it's simple. You can still do these easily by hand, but I would get in the habit of entering these as matrix equations. Just make sure that you know how to do that on your calculator. But the solution comes out to FBR is positive 14, 14.2 newtons, and the force vector on the body by the pin is positive 707.1, negative 707.1. Okay, so that one at first glance isn't quite as obvious, but it makes sense if you think about what's happening physically. this, so these two forces together have to counteract this force, right? But since this one can only acts as sort of a fulcrum for this end on the left also has to fight this rotational tendency produced by this one. Okay, so that's why you get that's why you end up with the downward force component at that left end side.
Isn't the Y component have the FBR in it too?
So yeah, that's right. So this force FBR, the force vector FBR, is just an upward. It's a 0x component and a positive y component of 1414. So it's pushing up. And yeah, I mean, mathematically, I mean, you could say that's the explanation. But like at your first glance, yeah, okay. All right, so these two examples, besides just sort of being practice at seeing we're going to do this type of stuff over and over again, you can see that setting up the free body diagrams and setting up Newton's laws depends on representing these joints correctly, right? If we, for example, had treated this joint as if it produced a couple, we would have ended up with an indeterminate system, and that's a problem. So solving these problems requires treating the joint loads correctly. So now I'm going to talk about how to know what loads are applied by what joints. Any questions before I go on to this about either of those two problems? So think of a joint as, like for our purposes, don't think of a joint as something that allows certain motions. Think of it as something that restricts certain motions, okay? So think of a joint as something that restricts the motion of some chosen body relative to another body. Often that other body is going to be the ground, but sometimes it's going to be, you know, something else. So what if there's no joint? What kind of motion is allowed by a body that's totally free? So a rigid body in 2D has 2 degrees of freedom in translation. So it can move in translation along the x-axis or translation along the y-axis. And it has 1 degree of freedom in rotation. It can rotate this way, okay? In 2 dimensions, this thing can't rotate about the x-axis or the y-axis. So this is 2D. In 3D, this is harder to draw. So say there's your X, there's your Y, and there's your Z. You have 6 degrees of freedom because you can translate along X, Y, or Z. You can also rotate about X, Y, or Z. So this one has a total of 3 degrees of freedom. This one has 3 degrees of freedom in translation, and another 3 in rotation. So that gives you a total of 6 degrees of freedom. To limit translational degrees of freedom, in either case, you have to apply a force, a component of a force, along that chosen axis. And to limit rotational degrees of freedom, you have to apply a couple component. Okay, so there are a bunch of types of joints that we're going to see a lot of. Here are some of them. Some you can use in 2-dimensional problems. Some only make sense in 3-dimensional problems. Some sort of make sense in either. So one that we're going to see a lot is a pin joint or a hinge. Those are really the same things. In 2D, you'd see it in a problem, something like that. Okay. So there's where the force is applied, right at that pin. In a 3D problem, you might see it something like this. So there's one body. And then there's the other one. Okay, so that's a hinge, and you could use that in a 3-dimensional problem. Then there are rollers. We'll see tons of those. You can have these in 3-dimensional problems too, but I'm not even going to try to draw that. But in a 2-dimensional problem, it'll look like this. There's fixed joints. We'll see a lot of those. I've already done a couple of those, but it'll look something like that. And then one that only makes sense in 3 dimensions is a ball and socket joint. So this allows one of these arms to rotate around relative to the other one, but they can't separate from each other in any way. So these aren't all the joints we'll deal with, but these are the most common ones that we'll see. And you can imagine that each of these, limits motion in a different way. We saw that with those two example problems. A pin joint limited motion in a different way than the fixed joint did. Okay, so what loads do they apply? To the chosen body? I mentioned this before, but remember that these loads are defined by the motions they prevent, not the motions they allow, okay? So that means when you think of a pin joint, don't think about the fact that it can rotate. Think about the fact that this body can't translate this way or this way, okay? And when you think of a roller, don't think about the fact that it can rotate or slide this way. Think about the fact that it can't drop into the ground or jump out of the ground in most cases. Okay, so first, let's go through some of the two-dimensional joints. And first, let's start with a whole set of things that these are all things that you'll see in drawings and they look different, but they all actually do the same thing mathematically. Rollers, frictionless surfaces, emphasize the less, because we're going to see friction surfaces with friction in a minute. A collar on rod, you know what a collar on rod is? Like this is rod. And I don't know, his mom doesn't trust him at the mall. Poor Rod. A pin in slot. And okay, so those are the ones that we're going to start with. Rollers, you'll see in pictures like this often. Like a little roller skate under something. You'll also see it as just a wheel. That's, I guess, what I ended up doing in my example. So those are rollers. Frictionless surfaces, you'll just see the surface and an object that ends like that, and it'll say something in the problem about it being frictionless. A collar on rod, a second definition, is you have something like this. Sliding over the rod. Okay, so this collar can slide up and down that rod. And then a pin in a slot. Will look something like this, where this pin allows this arm to slide back and forth. Okay. And mathematically, you treat all of these the same. All of these allow rotations, and they allow sliding back and forth. But I'm not going to write that because like I said, you don't want to think about them in terms of what they allow. Think of them in terms of what they prevent. So what they prevent is any kind of translation normal to the path of whatever the sliding, rolling thing. So what would you expect, what kind of load would you expect that joint to apply to the body? So the only thing it prevents is a known direction of translation. So it's just going to apply a force in that known direction. Okay. So the force component is going to apply a single force component perpendicular to the surface. Okay. Perpendicular to this path, perpendicular to this, the ground here. Okay. So the applied reaction load is a force in a direction normal to the rolling or sliding surface. That means that, often, like we had in our examples, that rolling or sliding surface is going to correspond with an axis of your coordinate system. And then you can just treat, like remember in the example, when I did this, when I used this roller, I just represented it with a y component of force. I could do that because my y-axis corresponded to the normal to that surface, okay? But that won't always be the case. So if it's not the case, then you have to do it using a unit vector and represent that force as a unknown, scalar variable times a unit vector that represents a normal to the surface. Anyone have any questions about that one? Okay, the next type is an object connected to another object by a cable or a link. So for a cable, you could have something like that. For a link, it could be the same thing. It's just that instead of a cable holding them together, it's just a piece of some metal that also can't be compressed. It doesn't have to be metal, obviously, but it just prevents compression in some way. And then I guess that means that this side also has to be connected to a pin joint like that. Okay, so that's a cable, that's a link. What kind of motions do these prevent?
One direction.
Yeah, right. It only prevents translation in the direction of that cable or link, right? Along a line, I don't know. There's got to be a better way to say this, but parallel to the cable or link. How about just along the cable or link? So it prevents a translation with a known direction. So that means that it's going to be only one force variable that we're going to use. So the applied load is a force parallel to the cable or link. Okay, so there's a difference between these two things. By the way, I'm not going to really go into how to do this, but I want you to sort of, because there'll be problems where you have to recognize this fact. The difference between these is if you try to push these two bodies together, the cable just folds and the link prevents it. Okay? So how do you think you treat that mathematically? You remember, I think you probably did stuff like this in physics. Well, actually, all you do is you calculate the tension, assuming that it's going to be in tension. Okay? So say you're trying to calculate the force this cable's applying to this body. Okay? Well, you know that the force has to be pointing this way, right? So you make that your unit vector pointing this way. Calculate the cable tension. And if you come out with a cable tension that is negative, then you know your system just isn't going to work. You can't build a system like that that's going to stay where you want it to stay. Okay? That's the only way to do it. It's sort of a case-by-case thing. So anytime you have a cable, you got to know that you're looking for a positive force only. And if you don't, you better look carefully to make sure something's not wrong. Okay? With a link, that's just not the case. With a link, you treat it the same way, but positive or negative values of that scalar variable are both acceptable. Okay? Because if you try to push this body towards this body, that link prevents it. Okay? Oh, actually, will you go back to your notes? On all of these, I want to just say how many variables we need to represent these. So go back to the rollers, frictionless surfaces. Okay, so with that first one, sliders and everything, pin in a slot, we have a force acting in one direction. So how many variables do you need to represent that?
One.
One. If you have a total unknown force vector, then it's two variables, right? If you can limit it to an unknown vector magnitude, but you know the direction, then you use a unit vector and you only need one variable. Okay, how about this one? Again, we have a force that we know the direction of, we just don't know the magnitude of. So it's going to be 1 again. The third type of joint is a pin or a surface with friction. These two are going to be treated mathematically the same. Everything is going to be treated mathematically. Mathematically the same is what I meant. Okay. So the pin joint will look something, we saw one of those already. Something like that. Surface with friction, it'll look just the same as a surface without friction. It'll just say in the problem that you have to worry about friction in this case. Okay, what motion does it prevent? That's right. It prevents translation in any, along either dimension, either axis, right? So any translation. And in order to prevent any translation, what kind of load do you need to apply? A full force vector, okay? Like if you only apply one component, then if you only apply one component of force, then you're free to move perpendicular to that force, right? If you apply two components of force, then you're restraining this thing to go this way, or any combination of those two, which is anywhere. So the applied load is a full force vector. And so therefore, how many variables do you need to represent that? Well, I'm doing all these as 2D joints, so just 2 in this case. Because it's 2 dimensions. Okay, so now I'm not going to go through these. The textbook has these all in them. But I just want to draw a couple of 3-dimensional joints, and I want you to work together, talk to each other, and try to figure out, I'll give you a minute or whatever, figure out what type of loads represent each of these joints. Oh, wait, sorry, I missed one. I missed an important one. Sorry about that. First, I want to do fixed joints. We'll see those all the time. So it looks like that. It prevents any kind of motion. So what kind of reaction loads does this apply? It prevents all translation, so we know it has to have those two, apply those two force components. It also prevents rotation, so it applies a couple also. So a full force vector and a couple. And so how many variables do you need to represent this one? 3, right. And notice this. We only have 3 equations in 2D, right? The only equations we have to work with are Newton's second law and rotational Newton's second law. So that means that if you have a fixed joint and you don't know the reactions, you can't have any other joints in there. You can't solve for anything else, right? Your 3 variables that go with your 3 equations are already used up, okay? So if you have something with a fixed joint and also a pin joint to something else, you know, you can't solve for that, isolating that body alone, okay? All right, now let's go to 3 dimensions. So first, how about a fixed joint in 3 dimensions? Looks something like that. What do you think the, think about it the same way. What motions does that fixed joint prevent in 3 dimensions? Everything. So what type of loads need to be applied to prevent any kind of motion in 3 dimensions? Yeah, all of them. So this time it's just 6, right? So I'll say a full force vector and a full couple vector. Anyone have any questions about that? Okay, second, how about a ball and socket joint? I just keep doing these because I like drawing them. There's the ball. Here comes the socket. Okay? So, what do you think about this one?
Just a 2D force vector, isn't it? Or it prevents everything.
Everything. It prevents every translation. So if it was only 2D, say, from this drawing, it looks like it might only be 2D. I mean, if you pulled on it, it looks like it would come right out. But say your coordinate system is like this, right? Think of it pushing in, and then it's pretty clear that it's going to prevent a translation this way, a translation this way, and it's going to prevent a translation at least in, hopefully out too. Okay? So, but it allows any rotation, right? Rotation about any of these 3 axes works fine with a ball and socket joint, right? So the load here is just a full force vector. So I skipped this step. For the fixed joint, how many variables do you need to represent that joint? Right. With the ball and socket, how many variables?
3.
Right. Yep. So third, ooh, this one's hard to draw. Um, okay, it's supposed to be a hinge. Yeesh. You know, a hinge. Why don't I leave these ends off? What do you think in this case?
Full force vector in the 1 couple.
Yeah, you're thinking right on the right track. So it actually, so let's put a coordinate system here and think about what's prevented. Translation. Most likely there's no translation allowed at all, right? Although actually you'll get some problems where they'll say don't count on this hinge to prevent a translation along this axis. Can you picture that? Like it'll just break if you load it that way, and like for like when your kids hang on the door and swing back and forth. That's why that drives you crazy, because hinges don't work very well that way, So translation-wise, you can treat that, depending on the problem, as requiring 3 force components or 2 force components. Okay. Does that make sense? Anyone want me to clarify that? Okay, how about rotations? So you said 1, and you're right, it does prevent some rotations. So think about, how about this axis? I didn't draw this super clear. Maybe because I put it in the wrong. Would this actually go like that? That? Who knows? But so say this axis is going right down the axis of the hinge, okay? Would it prevent rotation about that axis? No, that's what it allows, right? So we know that it prevents 2 rotation components. How about this axis? Picture, so that's like a twisting of this. You hold the 2 sides of the hinge like this and try to twist it like that. It prevents that, right? Although you could imagine maybe some types of hinges might be sort of flimsy that way. But for the most part, you can expect it to prevent that type of rotation. Now, how about you hold the hinge like this, there's the axis, and you bend it this way, okay? The other time you did this, like a torsion. This time you're trying to sort of bend it up. It'll prevent that. So everything is prevented. Every motion is prevented except rotation about the axis, okay? Unless the problem tells you don't count on it for this or that type of constraint. So that means that there are going to be three, or I guess how I've been saying it is it's a full force vector and two couple components. The one component that's not there is along the axis of the hinge. Okay, so next time we'll get into this problem using what we've just talked about. So say that you have a body connected to a pin joint. And connected to a wall with a cable, and you're applying a 1,000 Newton force at that angle, okay? And we're going to calculate the reactions, which in this case mean the force vector applied by this cable and the reaction loads applied to this pin joint, okay? And I have to get more practice problems up, solutions up. I did put up the solutions to the vector review. And I am also going to today put up the first problem set. One or two problems. I have to write it. So look for that today on D2L, and it'll be due a week from today. Okay. All right. Thanks. Have a good weekend. Have a good Monday off.